Someone's got to let
Good
me know.
afternoon.
Oh, thank you. Just to make sure you guys can hear me. All right, so you may have saw I've updated the exam date. So it was supposed to be Monday. I've moved it to Wednesday, and we wouldn't be able to get through the slides plus the examples I'd like to do, so I pushed back by a day. Okay, the exam, so that means we'll have today get through all the slides, and then on Wednesday hopefully get through all the examples, and Monday would have the review, and then Wednesday of next week would have the exam. Okay. All right, so we left off last class as we've gotten through most of this first set of slides where we learned about the internal flow and the general things, like looking at the entrance region and the fully developed region. We have the entrance region where the boundary layer hasn't kind of met, so it's still developing, and then it's fully developed after that. Okay, so we have that for hydrodynamic, so the velocity, and then the thermal for the non-dimensional temperature profile, right? So we have those kind of two situations there. And we then also looked at, since we don't have T infinity, U infinity, we have to have a mean. So we have a mean velocity and a mean temperature at each location in the flow as it's moving along in the x direction. Okay, so we looked at those equations, and then we had to figure out how we would determine those entry lengths, how long until they're fully developed in hydrodynamic and thermal. Okay, so that's where we bring back the Reynolds number, right? So we have the different versions of the Reynolds number that we went through, and then we defined what the hydrodynamic entry length is for laminar flow and what it is for turbulent flow, what the thermal entry length is for laminar flow, for turbulent flow, and our Reynolds number where it's critical, right? When it switches between laminar and turbulent for internal flow. Okay, so it's a different value than external flow. All right, then we said for fully developed, okay, we have a relationship for pressure drop and friction factor. Okay, so for laminar, we can get our friction factor equation right there. That's nice, and same for a turbulent flow for a smooth circular tube. Then if we have some roughness in the turbulent, we have to use our Moody diagram to get that surface roughness, but we can also get a pressure drop equation from it and power requirement to push that pressure change. So to overcome that pressure drop, what's that power requirement to push that fluid through? And then we looked at what that non-dimensional kind of temperature profile is to define when it's fully developed, and that's what you see at the top. And then we, showed and kind of talked about how the convection coefficient changes during the entry length, and then it becomes constant, okay, after it's thermally fully developed there. All right, then we already defined what mean temperature is when we're looking at the profile, right? When we're looking at the temperature profile, or mean velocity when we're looking at the velocity profile at a location, right? Well, how do we get how the mean temperature is changing from the inlet to the outlet? And that's what we did next, okay? So we used our equations to define the different cases. We have a case of a uniform surface heat flux. Okay, along that whole tube, we can get what the outlet temperature is from this equation. Okay, we can get our total heat from this equation. We looked at the uniform surface temperature. So now all along that tube, the surface is being held the same temperature on the tube. And we have our outlet temperature equation. Okay, so we can utilize this, okay, to get our outlet. And then our heat, total heat, is from this equation, which requires a log mean temperature difference. Oop, wrong way. And then we had uniform external fluid temperature. So this means now the fluid on the outside of this tube is what's being held constant, right? So it's not a uniform surface temperature. It's not a uniform heat flux on the tube. It's the outer external fluid is being held constant, having that same temperature, same velocity there, okay? So then we have a way to predict the outlet mean temperature. Here, we would need the total convection coefficient, or overall convection coefficient and surface area, or the total resistance, okay, from the outside convection to the inside. So we do a resistance network to get that overall convection coefficient, or our total. And again, the total heat transfer, we just use the log mean temperature difference again. All right, so then we should be right here. Okay, so now we have our first example is 8.16. And this one says water at 300 Kelvin and a flow rate of 5 kilograms per second enters a black thin-walled tube which passes through a large furnace whose walls and air are at a temperature of 700 Kelvin. The diameter and length of the tube are 0.25 meters and 8 meters, right, respectively. Convection coefficients associated with water flow through the tube and airflow over the tube are 300 watts per meter squared Kelvin and 50 watts per meter squared Kelvin, respectively. And then you see the schematic in the book, like you see on the screen, with the tube and the furnace. And then they say, part A, write an expression for the linear's radiation coefficient corresponding to radiation exchange between the outer surface of the tube and the furnace walls. Explain how to calculate this coefficient. The surface temperature tube is represented by the arithmetic mean of its inlet and outlet values. And then part B is determine the outlet temperature of the water. So the mean outlet temperature. So that's what you see here. Part A is really required to get part B. So they're just kind of helping you out to get part B by telling you what to get in part A first. But we have to get this outlet temperature of the water, right? So we know the inlet right here coming in. We have a mass flow rate of this tube. We have the furnace, and the furnace has this walls. The walls of the furnace at 700, air 700 Kelvin also, and we need to get the outlet temperature, okay? So which condition here do we have? Is it the uniform surface temperature? Is it the uniform heat flux? Or is it the uniform, or the the external fluid temperatures, or external fluid conditions are being held constant? Which of those three conditions is going on?
External fluid temperature.
Yeah, so we have this furnace, and in a furnace you might have a thermocouple measuring the air temperature, and you're controlling that furnace to 700. Just like in your house, you don't have a furnace in Florida, but you're controlling that thermostat is controlling it to a temperature, so it's controlling the air, right? It's not controlling the hot water pipe that's going through your house. That pipe is still hot, right? Still not at that air temperature, so it's got a different temperature. So it's the air, of the furnace that it's controlling, and we also say the furnace walls of 700 in this problem was given. All right, so we know then it's external. It's that external fluid. We also know then if it's the external fluid, it can't be constant heat flux on the surface, right? Because this temperature is changing from here to here, but this temperature is being held constant. So the heat transfer initially is going to be very high over here, right? Because you have 700 and you have 300. Well, this water is going to get warmer by the time it gets to the end. So now your heat transfer rate at this sliver of location, your heat flux is going to be lower. So your heat flux is changing. So you can see that it's not constant heat flux, right? Or temperature is not going to be held the same. Since this is changing, this is being held the same, but this temperature is changing from here to here. That means that surface temperature right here to here is going to change too. So we don't have constant surface temperature in this situation. What's being held is that external fluid. So external fluid is being held constant. So we have this case, okay? So that means to predict the outlet, we need mass flow rate, which was given. We need to get properties of CP. And we either need to do it with the overall convection coefficient or the resistance. So we either use this or this and set it equal to our temperature change, okay? And in this problem, they use R total, okay? So we'll use that version. Okay, so we see our equation that we just picked out right here, okay? So here's that equation. We're looking for the outlet temperature. We were given T infinity, inlet, mass flow rate, so we need CP and R total. So our R total is now where you see it here, but that's where we set up our resistance network, and that's what you see being done right here. Okay, so we have here is our mean temperature. Okay, so this is inside the fluid, so that's from here to here. So we're basically setting it up at this point right in the middle, okay, at the average we're taking. All right, so then we have our convection internally to that wall right here. Okay, and the wall surface is changing. So again, we have the tube average temperature. Okay, and we're assuming it's thin-walled black surface, so that means it's got negligible resistance due to conduction. Okay, and if you have a metal tube, that's pretty common because metal transfers heat very well compared to convection, so that usually the resistance is negligible. Now, if we had insulation or something like that, now you got to take that into effect. But with it being just a metal tube, it's neglecting that resistance. All right, so then we have a parallel circuit in this case. So we have convection from the outside of this tube to the fluid air in the furnace. And then we have radiation from the outside of the tube to the furnace walls. Okay, and we're using the R for convection resistance and the resistance for radiation in this case. And that's why they asked in part A to linearize the radiation, which is back from chapter 1, where we have equation 1.9, where we use a radiation kind of coefficient. All right, but it's dependent upon, we have the furnace temperature, right? But it's dependent on the tube temperature. Okay, it's dependent upon this, right? All right, so then if we go back again, we need that R total. So our resistors, these are our resistance networks. So to get R total, we just set up, and that's what you see here, is you're adding, you have a series resistor, and then you have this parallel circuit. And that's what you see here, the convection internally, and then here's the parallel circuit, okay, to get you the R total. So then we need equations for each of these resistances. So if we go back to where they start, each of the resistances, we have convection internally. They gave us the convection coefficient in this problem. The external convection, they gave us the external convection. So surface area is easy based upon geometry. So then the tough one is the radiation, right? So we have our equation. So we need that H radiation, which is our equation here, okay? So to get this one, all right, we need that tube temperature. And the tube temperature is solved from circuit. Okay, so if we set up our equations of the thermal circuit, you have this temperature difference, and then you have this temperature difference. Okay, and that's what you see here. This is the temperature difference right here, equal to the temperature difference on this side and the resistors from it. And that sets up an equation to solve for that tube wall temperature. Okay, so that gets us the tube wall temperature. We have the furnace temperature, we have convection resistance, so we have the tube temperature. So the last thing we need is the mean temperature, which is just the inlet temperature, which is given, and the outlet temperature, which we're trying to solve, so we don't know that yet. Okay. All right, so there's a lot of equations on here, and a lot of that one thing depends on the other, which depends on the other. So the best way of solving this is really guessing an outlet temperature. Okay, so if we started here and guessed an outlet temperature, okay, and then that would get us the mean temperature. Okay, if we go here, mean temperature, we can use this to now, if we have the mean temperature, we can use this to get the tube temperature, okay, which we can also then utilize to get our radiation coefficient, and if we have the mean temp, we would have to guess this initial tube temperature too, but we basically are guessing, and then all the equations will go through and solve for our new outlet temperature. Okay, so we'll get a new outlet temperature. Okay, so then we just recheck our mean, check our mean temperature that we guessed initially. And so maybe we go through and we have to do another iteration. Okay, but if we go through and do it enough, maybe it's one iteration, maybe it's two, maybe it's three, we're going to end up that nothing's going to change, and we're going to get these as our answers. Okay, and the outlet is this temperature right there. Any questions? So it's similar to what you have to do in machine design, right? A lot of things depend upon a lot of other things. So you got to just basically guess, solve, check, and go through again, right? All right, so we're on the next set of slides from Chapter 8. And this deals with the correlations, okay, for internal flow. So the last one dealt with the overall understanding of entrance length, fully developed, how to get outlet temperatures, knowing the inlet, and how to get that total heat transfer, okay? Now this deals with getting that convection coefficient, right? We haven't talked about how to, for internal flow, how do you get that Nusselt number and convection coefficient, okay? So we have these different considerations. So if we're fully developed, right, we determine that our length is greater than the entrance length thermally and the entrance length hydrodynamically, so we're fully developed flow, okay? So in those situations, now we have the equations being shown here. We have for laminar, okay, circular tube, so we're going to start with that simple geometry. We have the conditions then of uniform surface heat flux, so that's if you have kind of an electric heater being applied, you get a nice, just constant value of 4.36 for Nusselt number. And same with uniform surface temperature, you get a nice constant value, but it's 3.66 for the Nusselt number. This is laminar flow, fully developed, right? Circular tube. Now we go to turbulent flow, right? Still a circular tube. We have extra conditions here, right? If it's a smooth surface, fully developed turbulent conditions, we have a nice equation right here. There is two conditions. If the surface temperature is greater than the mean temperature, so the fluid's being heated, right? So the wall temperature is basically hotter than the fluid temperature. That means heat's going into the fluid, right? If the fluid is greater than the surface temperatures here, this is the fluid is being cooled, right? So that changes that parameter n. Okay, so that's a small detail, but it's one I see as a mistake quite a few times, because you might just grab it from another problem and it might have used 0.3 or it might have used 0.4 and the temperatures were different. It was a cooling problem and you're now doing a heating problem. Okay. All right, so now if it's not a smooth surface that we can assume, it has wall roughness. Now we have to use an equation for the Nusselt number that has the friction factor in it. Okay. And we can get our friction factor different ways with the Moody diagram, right? All right, so this now talks about non-circular tubes, okay, because all these dealt with circular tube, okay? So now if the tube is not circular, we have the hydraulic diameter, okay? And then for laminar flow, we have a nice table, 8.1, that gives us our different Nusselt numbers based upon the different type of non-circular tube, whether it's square, rectangle, a triangle, different values there, okay? And for constant surface temperature, constant heat flux. For turbulent flow, we can just still use the equations we see here, okay? But we're just going to use it at the hydraulic diameter. Okay. All right, so now we're switching to issues with the entry length. So now the fluid is not fully developed, right? The length that when you check what the entrance length is, your tube length is less than what is required for the flow to be fully developed. Okay, so we get this situation of now we're in the entry region, okay? So if we look at our curves here, it looks very similar. This is showing you this parameter, the Gratz number versus the Nusselt number, okay? And we've seen this kind of curve in the last set of slides where it showed the convection coefficient, which is basically what the Nusselt number is. When we showed once you hit fully developed, same value, right? Well, this is kind of showing that with actual values now to it, okay? So we have these two conditions on this figure, okay? And there's also, this figure is 810. We have figure 810A is for the local Nusselt number. B is for the average Nusselt number, okay? So if we end up getting this Gratz number and we're over here, we're fully developed, which just goes right along with what we have to check for whether you're fully developed or not. You get that constant value for surface, constant surface heat flux, constant surface temperature. Now, if we get our value and we're in this entrance region, we find that we're at this point. Now we can, pick our point here, okay, for those different conditions. The one thing that's on here is we have this combined entry length and we have this thermal entry length. The combined is if the thermal and velocity modulators are developing at the same time. Okay, so we have a tube, they're both inlet temperature is uniform, velocity is uniform, and now they're developing at the same time. So let's say we have Prandtl number near 1 or 0.7 in this case with the solid lines. Okay, so they're both developing at the same time. So then we have this condition of these solid lines here. Okay, the thermal entry length line, this dashed lines, are the situation where the hydrodynamic, the velocity, is fully developed, but the thermal is developing. And what we can do is we can do this for Prandtl numbers that are much greater than 1. We can use and just look at the thermal entry lengths. Okay. And we talked a little bit about this in maybe it was chapter 6 of Prandtl numbers, or maybe it was the earlier chapter. Prandtl numbers. No, we didn't. No, it was the first set of slides in this chapter. The Prandtl number tells us about the ratio, right, of the velocity boundary layer thickness to the thermal boundary layer thickness. And so if we have a Prandtl number much greater than 1, what is that telling us about the velocity boundary length or entry lengths, right? So let's go back. This will maybe help. So if we're here and so we're just looking at the laminar condition to keep it simple. If we have a Prandtl number much greater than 1, right? So 100 or 1,000. What's that telling us about the thermal entry length compared to the hydrodynamic entry length?
The Prandtl numbers.
The Prandtl number. So let's say the Prandtl numbers, let's say it's 100 or 1,000, let's say. So what is it telling us about these different lengths then? I didn't quite get your response. Any answer?
It should be 1,000 times larger.
Yeah. Okay. So this is the only time you see that Prandtl number there, right? So that's 1,000 times. This is right here is the same value here. Okay. So the Prandtl number makes the 1,000 Prandtl number makes the thermal entry length 1,000 times longer than the hydrodynamic, the velocity. So with that being 1,000 or 100, that length is so much longer that you got to wait on the thermal that the hydrodynamic is already fully developed, and we can just assume it was fully developed the whole time because it was such a short distance compared to the thermal that we can just say it was fully developed hydrodynamically the whole time when we have large Prandtl numbers. Is what this line, the dashed lines, are for. All right, so we have then also equation versions. So this helps us, a table that I just showed, or table, I think I probably wrote table. No, all right, figure 810b, right? If we're looking at it here, it has combined at 0.7 Prandtl number. Well, here's combined, but you can input for any Prandtl number. So that one just showed it for 0.7, which is, kind of you can use this line, then this solid line in this plot for air, because air is right around 0.7. So we could use this figure instead, or we have this equation that works for any. This equation looks like a fun one, right? You'll be typing in your calculator forever and making a whole bunch of mistakes, right? And then we have the thermal entry length. So this is when we have those very high Prandtl numbers, right? So there's no Prandtl number then inserted in here. Okay, so that equation is like looking at the dashed line here. Okay, so then that was this was all dealing with entry length, laminar flow, circular tube, right? These two slides. So now we're changing to turbulent flow, still circular tube. Okay, average Nusselt numbers. It's not as pronounced for turbulent, so a lot of times we can neglect it, but we have some justifications here. So if it's a very long tube, L over D greater than 60, we're just showing the Nusselt numbers kind of the same as the fully developed. Or if we have a short tube, we can make a correction. Okay, so we can take the fully developed value and correct and get our actual value with this kind of equation right here with C equal to 1 and this M parameter to 2/3. So it just kind of corrects the Nusselt number for shorter tubes. All right, so now if we switch to non-circular tubes, it gets a little more tricky, right? And that's where the book starts pointing you into other references, maybe journal articles or books that are more in depth on that area. Okay, so non-circular tubes and looking at this entry length. Turbulent flow, we can just take and kind of use the hydrodynamic diameter as our first approximation. One other thing to be aware of is where do we get our property values from, okay? And for the average Nusselt number, we're going to be looking at that mean temperature of the tube. So we're going to be taking the inlet outlet, dividing by 2, so getting our average, and then using that to get our properties, okay? There is a correction. So let's say we have a liquid, let's say like oil, and what can happen is if you're looking at, let's say, one point within this tube right here, and we have a temperature here, surface temperature there, you have your mean temperature here, here's your surface temperature, right? Well, with some fluids, particularly liquids, let's say oil, your temperature from your mean to your surface might only be 100 degrees Celsius difference or 100 Kelvin, but the properties have large variations. It might be now an order of magnitude difference in viscosity, let's say, not just 100 more, or it might be orders of magnitude difference. So now you might want to look at correcting for that property differences. And that's what you're seeing here is we have the Nusselt number we calculate, and then we're correcting to get this one based upon the large property variations that you get from basically this is at T mean, and this is at the surface. So although T mean and the surface temperature might not be that far away from each other, those viscosities might be far away from each other, because overall the viscosities are what causing a lot of the effects and not just the temperature. One other thing to note is internal flow problems, as you've seen in the first example and how I'm mentioning things, is you're going to often require iteration, right? Because you might not know the outlet temperature, but you need the mean temperature that's a function of the outlet to get your properties, right? So a lot of times iteration is required because of that. Here's more of a special situation. This is with concentric tubes. Okay, so that means we're having kind of fluid flow in this concentric tube here. So you have an inner diameter and an outer diameter of where the flow is, and there's a surface temperature on the outside surface. and then a surface temperature on the inside. Okay, so it's a special situation of looking at this kind of the heat transfer in this situation, the Reynolds number and Nusselt number. We look at it with the hydraulic diameter, which is just the difference between the two diameters. Okay, and we can grab fully developed Nusselt numbers in tables 8.2 and 8.3. Turbulent, we can just use the values based upon the hydraulic diameter for a circular tube and use those for the concentric tube. And then there's a few other ones that we're skipping over that goes into more detailed for specific geometries within the chapter. All right, so moving on to the examples, we have 8.41. The air passage for cooling a gas turbine vane can be approximated as a tube of 3 millimeter diameter, 75 millimeter length. The operating temperature of the vane is 650 degrees Celsius, and the air enters the tube at 427 degrees Celsius. For an airflow rate of 0.18 kilograms per hour, calculate the air outlet temperature and the rate of heat removed from the vane. And then part B is generate a plot of the air outlet temperature as a function of the flow rate for 0.1 to 0.6 kilograms per hour. Compare this result with those for vanes having 2 and 4 millimeter diameter tubes with all other conditions remaining the same. So part A is one situation. They want the outlet temperature and the rate of heat removed. Part B is a parametric study on how mass flow rate and the tube diameter changes the outlet temperature. All right. So we have this gas vane, right? So we have exhaust gases on the outside. Okay. We have air coolant passageway through it. Okay, so inside here is a passageway. Okay, and they're saying the vane itself is at this temperature, okay, which is 650. So now we have our tube. We have our inlet temperature given, mass rate given, and we're looking for that outlet temperature. We're also looking for the rate of heat removed from the vane. Okay, so we want the outlet temperature and the heat. Okay, that's right. Okay. All right. And then part B is that parametric study. Okay. So we're looking at the schematic. Which situation do we have? Do we have constant heat flux, constant surface temperature, or constant external fluid temperature? Anyone want to take a guess there? What's being held constant here on the boundaries? On the boundary.
Is it the surface?
Yeah. So it tells us in this problem, although we have gases on the outside, right? So it could have been that, but they don't give us anything about the gases, and they just say the vane is at 650. So that's this whole thing. So the metal is at 650, and it has air flowing through it. So that means the surface temperature is constant. Okay. So we have that case. Okay, so let's go look at that case in our first set of slides. All right, so here's uniform surface heat flux. So we don't have that one. We have the uniform surface temperature, right? Okay, so we developed this equation in the lecture last time. So we have then to get the outlet temperature, which is that right there. We're given the surface temperature, inlet, right? And over here we can utilize surface area. So from geometry we can get that. We have to get the average convection coefficient still. Mass rate was given, and then CP we got to get from our properties. Look that up. Okay. And then total heat rate, which the solution doesn't go into, but the problem asks, is just from this equation. Okay, so if we have the outlet temperature, we can utilize this delta T, the log mean temperature difference, so this one and this one, and just plug it, get the log mean temperature difference, and then get that. So once we have the outlet temperature, we can utilize those two equations below it to get the heat. All right, so let's go through the steps here. So here's our equation that we just showed, right? Getting the outlet temperature, given this, this, and then perimeter and length. We have the perimeter now. Length was given. Mass rate was given. CP is if we assume a mean temperature. So again, this is the inlet plus the outlet divided by 2. Okay, so they're assuming to get the properties like CP that we just needed. Okay, so we have CP. So now last we needed the convection coefficient. So we have circular cross section, get our Reynolds number, we get 584. So the flow is laminar. Now we got to see whether we're fully developed or within the entry length. Okay, so we go and grab our equation from the first set of slides for the entry length for laminar flow. Okay, and that's this equation right here. It was X over D in the slide, but they're just rearranging it. Okay, so they're just rearranging it to solve for this, right? And we get 88 millimeters, and our length is 75. Okay, so the entry length required is greater than our length. Okay, so that means we're not fully developed, right? We're in the entry length, and we're in the combined version. So it's not just the thermal entry length, because the Prandtl number is close to 1, right? We're not in that Prandtl number that's very much larger than 1. We're near, we saw where we looked in the properties, we're at 0.7. So very close to 1, all right? So that means the entry lengths are developing very close to each other. Okay, so we're in the combined entry length region. So that means we got to go to our slides with that. Okay, so we have entry region, laminar flow, circular tube, combined entry length. Okay, so in this case, our Prandtl number is very close to 0.7, so we could use this figure to get there, or we can use this equation right here. Okay, figure is really good if you just want to calculate it once, right? Equation is really good if you're putting it into something like MATLAB, doing a parametric study, doing design, because you don't want to keep looking something up in a figure or table when you're trying to iterate design, right? So we have this equation. We have to get the Grotz number, which is this. Okay, in our situation, it's the full length, so X becomes L, and we can solve for that. Okay, so let's see. And that's what you see right here. So they're getting the Grotz number at X equals L. We have the Reynolds number, Prandtl number, we get 16.5. So we can either utilize that figure right here, or utilize the equation, right? So in the equation, the Gauss number, Prandtl number, right? So they haven't solved directly for the Nusselt number. They rearranged, solve for convection coefficient, and that's what you see here. This is K over D, and all this inside here is the Nusselt number. And doing all that and hoping you put everything correctly in your calculator, you get 95 as your convection coefficient through the tube, the average convection coefficient, 95 watts per meter squared Kelvin. So we go back to our equation up here. Now we have the convection coefficient, solve for our outlet temperature, and we get 585 degrees Celsius. And then we can check our mean. We're checking our guess from right here. Okay. All right, so then part B, they're just varying the mass flow rate and they're varying diameter, okay? And so we see the single curve here. And what's happening is we have a single curve, even though there should be 3 curves for the diameter, so for 2, 3, and 4 millimeter diameter. And what it is all those curves are on top of each other. So there's independent from diameter, but mass flow rate has the dependency. So diameter is not changing things, but the mass flow rate is, okay? So we have, very slower mass flow rate. The air ends up going from, 427 to that above that 600, right? Very high mass flow rate. It goes from 427 only to, like 425 or sorry, like 410. So it's going so fast through the tubes, the air is not heating up, right? But we could also calculate what this is to heat, right? That was with that log mean temperature difference. Okay. Any questions? All right, so then we got another one to do. We got 8.48. 8.48 is exhaust gases from a wire processing oven are discharged into a tall stack, and the gas and stack surface temperatures at the outlet of the stack must be estimated. Knowledge of the outlet gas temperatures, TMO, is useful for predicting the dispersion of effluents in the thermal plume, while knowledge of the outlet stack surface temperature, TSO, indicates whether condensation of the gas products will occur. The thin-walled cylindrical stack is 0.5 meters in diameter, 6 meters high. The exhaust gas flow rate is 0.5 kilograms per second, and the inlet temperature is 600 degrees Celsius. Part A is consider conditions for which the ambient air temperature and wind velocity are 4 degrees Celsius and 5 meters per second, respectively. Approximating the thermophysical properties of the gas as those of atmospheric air, estimate the outlet gas temperature and stack surface temperatures for the given conditions. And then part B is a parametric study on the wind velocity, so varies the wind velocity and the ambient air temperature. And we'll see how that changes the outlet gas temperature. All right, so we have also the schematic that you see right here on the screen is what is given in the problem. So they tell us an outlet gas temperature, or an oven gas temperature, say and that would be our our mean inlet temperature, okay? And then they tell us ambient air temperature and a wind velocity, okay? And they want us to solve for the mean outlet gas, exhaust gas temperature and the surface outlet, the temperature on at the surface and the outlet, okay? So those two temperatures are what they're wanting, okay? And they gave us mass flow rate in, they gave us temperature in, they gave us geometry. All right, so let's start with what situation do we have? Do we have the constant heat flux? Do we have constant surface temperature? Or do you have a constant external fluid temperature? Anyone want to give a guess here? What's being held constant externally on this situation?
The outside temperature.
Yeah, so the outside temperature, right? Our ambient conditions, right? That's being held constant, right? So if we thought about it here, like at the inlet, right? And we did a thermal circuit, here's T infinity, we have convection on the inlet, we have, so let's do it this way. Resistance from convection on the inlet, we have the wall, and then resistance convection on the outside, okay? Usually this wall we can neglect, okay? It didn't have any insulation, so we're gonna end up neglecting that, okay? So it's a metal tube, we can say its resistance is small compared to convection, okay? So if we look at it here at the inlet, this temperature is the mean inlet, and then infinity, T infinity is staying the same. And then if we looked at it at the outlet and have the same kind of idea here, again, cancel that. As the exhaust is going through the stack, the temperature of that exhaust is changing, right? As we're going from here to here, the temperature is changing of the exhaust. So because it's cooling as it's going through, because T infinity on the outside is cool, right? So it's changing temperature. So that means as we're going through, the wall temperature is going to change, which is that case right there. And the heat flux would change because this resistance circuit is telling us about heat, right? That's what's telling us about what heat is going into this resistor. So our heat flux would change as we work away from the inlet to the outlet. Okay. All right, so we have then constant external fluid, as was said. So we have it's not our uniform surface heat flux, not uniform surface temperature, uniform external fluid temperature. Okay, so we have this case, right? And we can either, for the outlet temperature, we can either use the overall convection coefficient or basically the R total, right? And in this version, we're going to use the overall convection coefficient. Okay. So we have T infinity, we have the inlet temperature, mass flow rate was given, so we just need geometry, the surface area that convection is occurring on. We need our specific heat, so again, properties lookup. Okay. So that's to get the outlet gas temperature. How do we get the surface temperature right at the outlet? So how do we get this temperature now? The surface right here. Temperature right there. Because this TMO is the mean temperature at the outlet. We want now the temperature right at that surface. Any guesses?
Do we use the mean temperature?
We use the mean temperature, right? So we'll use this temperature, not the mean from the inlet to the outlet, but the outlet's mean temperature right here. So if we know, let me redraw the resistance network because I have some stuff messing it up. So at the outlet, if we know the outlet's mean temperature, and then we just have our resistance from convection on the inside, and then we have resistance from convection on the outside to T infinity. So this would be our resistance network right at the outlet. If we have the outlet mean temperature, we have T infinity, we get our resistances, we can just use the thermal circuit to solve for the temperature at the surface. Okay, because we'll have this, we'll have T infinity, we get our T surface outlet. All right, so here you see, let's make this bigger. They're redrawing the schematic. Again, showing you the mean temperature we're getting and then the surface outlet. We know the inlet, mass flow rate, geometry, and we go through, have some assumptions, steady state, right? Negligible wall resistance, right? We're saying it's kind of thin wall, or the metal has just got a high thermal conductivity, enough that makes that resistance very small, okay? We're neglecting radiation, okay? And constant properties we have, okay? So we have some down here, we see some properties. They're again assuming an outlet to get a mean, right? Because got to average to inlet and outlet, okay, and you get you your mean. The other thing we see is there's a whole nother set of values calculated, and that's because we have external flow also. So this side is flowing around that cylinder. So we have external flow. So we have basically a chapter 7 problem and a chapter 8 problem here, right? So you have the outside, which has T infinity and the surface temperature on the outside, and that's where they're getting these set of properties. And then on the inside, we have the mean temperature, so that's where we're getting these sets of properties. Okay. All right, so let's go through those steps now with the equations. We have our equation we found for because of our external temperatures being held constant, right? We know this perimeter is pi d. Okay, so we'll know that. length was given, mass rate's given. Now we have our properties. So we got to get our overall convection coefficient. And that comes from the thermal circuit, okay, and our equations from chapter 3, okay. And here it ends up coming to be that. So that means we need our internal convection coefficient and our external. And the internal, we have internal flow. The external, we have external flow around the exhaust stack. So internal flow, we go and check our Reynolds number. We get about 34,000, right? So it's turbulent. And it says assuming fully developed conditions, but we can check that, okay? So if we look at L over D in this case, and we get 6 meters divided by 0.5 meters. Check. Yes, 6 divided by 0.5, which would give us 12, which is greater than the 10 we said we would use for turbulent flow to decide whether we're fully developed or not. Okay. So we're fully developed. All right, so we have fully developed turbulent flow. So we go and grab for internal, and we go through our equations. We have a circular cross section, fully developed, turbulent flow, fully developed, circular tube, and we have for smooth surface, we can assume, we have this equation. So we just have to grab the right, whether the fluid's being heated or cooled. In our case, it's cooled, so it's 0.03. So we grab this relationship for Nusselt number. All right. And you see here, all right, we have our Nusselt number equation pulled. And we can utilize this in this equation to solve for the convection coefficient. So we get 10.2. And now we have external flow. Okay, so this is just like cross flow over a cylinder from chapter 7, right? So we have flow over a cross flow over cylinder, and we get our value, right, for Reynolds number, and then we can utilize our equation for cross flow of a cylinder. We get a Nusselt number of 205. Rearrange it for the convection coefficient, we get 13.2, right? So now we have our convection coefficients, means we have our overall convection coefficient. So now we can solve for our outlet mean temperature. So we do that, we get 543 degrees Celsius. Last is that outlet stack surface temperature, where we said we'll just use the thermal circuit. They're showing it with energy balance, same as thermal circuit. Okay. So we know this, T infinity. We now know the outlet mean temperature. So utilizing our relationships of our delta T's here between this and this, or across the whole thing and this, we have a way to solve for that surface temperature at the outlet. Okay. So we rearrange, solve, we get 232 degrees Celsius. Last part B is that parametric study. So they have the air temperature changing. So we have a really cold day in Florida, and it's negative 20 degrees Celsius, right? And then a different day, we have let's just say it's the same day in Florida, and we have 35 degrees Celsius, right? So they've trended lines for those different conditions. Here's what the exhaust gas outlet temperature would look like with the air temperature is 35 in the afternoon, and in the morning it was negative 25 degrees Celsius. That's what our curve would look like with different wind velocities, right? So then we can play around with what that exhaust outlet temperature looks like at these different situations. And then in the practicality, they use this to look at what that means, the plume coming out of that exhaust stack, and what that might mean to the environment, looking at what's going to happen to that plume as it exits, where is it going to go, how does it disperse, and then the other one that we solved for was that outlet surface temperature, right? And that's where we got this 232. Well, this is, you don't want anything in the exhaust to condense or to precipitate out. So let's say you were looking at this condition and the outlet was too cold that water would condense. So now you got water droplets potentially falling back into your system, okay? And that's not necessarily a good thing. So then you got to take care of that with a collection, or, if you don't, it could damage your system. So that's where you try to keep anything then above that, above the temperature where it could condense out. Okay, so I do this in my studies. I have to keep everything where I take an exhaust sample greater than the temperature that the water would condense out or do. So then water doesn't condense out and change all my readings of what that exhaust sample looks like, because I wouldn't have the water in my sample now if it's condensing out. So that's one of the things that they kind of look at, and that's the practicality of something like this. All right, any questions? Or the same thing happens in the morning when you see water droplets come out of your exhaust pipe on your car. That's because it's too cold and the water's condensing out as water and not leaving your exhaust pipe. So you see water droplets stripping out. Okay. Any questions? All right, so then we'll do examples all next class. I'd like to get through all 3 examples in chapter 8 next class. All right, so that's it for today. You guys have a good rest of your week until you see me again on Wednesday, and then you'll have a good rest of the week after that too, all right?
Thank you.
Yep, thanks.